these problems can be some of the more difficult word problems just because of the setup. So what I'm asking is that for each of the following problems, you read the situation carefully twice. Look at what the question is asking, then define your variables with very clear let statements, set up the equation so that I can see and give partial credit if something goes wrong, solve whatever equation you get, and finally state your solution in a complete sentence. That last part is simply because you need to make sure you've actually answered what the question is asking. So let's start. One number is 3 times another. The sum of their reciprocals is 4/9. Find the numbers. One number is 3 times another. Okay. I can use one or two variables here. It really doesn't necessarily matter. But why don't I start with saying one number is x and 3 times another. So another number would be y. And I'm going to say let x and y, I know this is cheating a little bit, equal the numbers. So if x and y are the numbers, and one number is 3 times another, then my numbers, like my first equation, could be x is equal to 3y, and then it says the sum of their reciprocals is 4/9. So the reciprocal of the first number, let me move this over here, the reciprocal means 1 over x and 1 over y. So the sum of their reciprocals is 1 over x plus 1 over y is equal to 4/9. And this can be my system if I want to use two equations. I only say that because sometimes using two equations makes the process a little bit easier in the setup. So now this is going to be a substitution. I'm going to take this and substitute it down there and build a single equation that I'm going to want to solve. 1 over 3y plus 1 over y is equal to 4/9. This now harkens back to the rational equations we've been solving over the last couple of days. So the LCD for this, the least common denominator, would be 3y. Nope, there's a 9. It'd be 9y. And I want to multiply both the left and the right sides by that 9y. So if I multiply the left side by 9y, the 9y is going to distribute. It's going to divide with the 3y to give me a 3. And I get 3 plus, then it's going to divide with the y, and that's going to cancel that out to give me a 9 equals 4y. So I get 12 is equal to 4y, which means if I divide both sides by 4, I get y is equal to 3. Since x was equal to 3y, as we saw right up here, that means x is equal to 3 times 3, which is 9. So then I can just say the numbers are 3 and 9. In the next problem, two families from the same neighborhood plan a ski trip together. The first family is driving a newer vehicle and makes a 330-mile trip at a speed 5 miles per hour faster than the second family, who's traveling in an older vehicle. The second family takes a half hour longer to make the trip. What are the speeds of the two families? So, once more, we have two families planning a trip. Fine. First family is driving in. Okay, fine. First family makes the 330-mile trip at 5 miles per hour faster than the second family. So, this is telling me that I should let r equal the speed of the second family. And because of the units, I'm going to do this in miles per hour. And if the other one is 5 miles per hour faster, that's going to be r plus 5 is the speed of the first family in miles per hour. So that gives me the rates of the two. Now let's look at what we can conclude about the times. Hold just a second. So now we're going to build a rate time distance table with this because that's just an easy way to visualize what's happening. So my rate as the first family, we have r and r plus 5. The distance is 330 for both. And the time, I don't know the times. I know that the second one is a half hour longer. But what I'm going to do is I'm going to express time as distance divided by rate. I know that if rate times time is equal to distance, time is equal to distance divided by rate. The cue for you guys should be that a lot of these deal with variables in the denominator. So that should be a clue to you guys that your equations are going to have variables in the denominator. 330 over r and 330 over r plus 5. And this is the speed of the fast family, and this is the speed of the, oh no, sorry, this is the slow family, and this is the fast family. So then it says the second family takes a half hour longer. So that means the time of the slow family, I'm going to write this down, time of slow equals a half hour longer plus the time of the fast family. Well, I'm going to use that to build the equation. 330 over r plus, or equals a half plus 330 over r plus 5. Now this is the equation we have to solve. So I'm going to multiply the left side and the right side by the least common denominator of, I have a 2, an r, and an r plus 5. If I do that, then I get, let's see, multiply it here, the r clears, and I have 330 times 2 times r plus 5 equals, multiply that here, I have r times r plus 5 plus 330 times 2 times r. So keep track of all that. It's a lot to watch when you're multiplying by least common denominator, but you can get it. Oops, that was a stray mark. Okay, now let's simplify both sides as much as we can. So 2 times 330 is 660. So I have 660r plus, then I multiply 2 times 330 times 5, which is 3300, equals r squared plus 5r plus 660r. You're going to notice the 660r's cancel because if I subtract that from both sides, and then we're going to set this equal to 0, so I get r squared. Oops. Don't glitch while I'm recording. And we're going to do this before we get to class. Okay, r squared plus 5r minus 330, or 3300, is equal to 0. Okay, now the trick is to try to factor this. And that's going to be a little bit tricky. I know that if I start splitting this up, I get I can do 33 and 100. Those don't differ by 5. I could multiply the 33 by 2 and get 66. Divide that by 2 and get 50. That's not quite where it needs to be. If I divide this by 3, I get 22, and multiply that by 3, I get 150. That's not quite, we kind of have to keep playing with the numbers. Divide that by 2 and get 44, and I'm going to pause while I run to class. I know that 44 is a factor of 11, so I go 11 times 4. I know 75 is a factor of 5. 5 times, that's 5 times 5 times 3. And if I bring this back, let's make these two go together, so I get 55. And then 4 times 5 times 3 is 60. Boom. 55 and 60 actually work. So I would factor this into r plus 60, and r minus 55 is equal to 0. This means that r would have to be 55 because r can't be negative 60. And so then I would kind of complete this. The speeds are 55 miles per hour, and the other one was r plus 5, so 60 miles per hour. The next problem harkens back to the river current problems that we've been talking about earlier. So anytime you see, well, let's read it. A boat travels 26 miles up a river in the same amount of time that it takes to travel 34 miles down the same river. the current is 2 miles per hour. What is the speed of the boat in still water? So if I read it again, a boat travels 26 miles up a river. It's probably going to, or in the same time it takes to travel 34 miles down the same river. The current is 2 miles per hour, and the speed of the boat in still water is a variable. So we're going to let B equal the speed of the boat in still water, and that is going to be in miles per hour because those are the units the problem's using. And the current is 2 miles per hour. So if I go upstream, I know that upstream I'm fighting the current, so the speed of the boat minus the current. If I go downstream, I'm getting a boost from the current, so that's the speed of the boat plus the current. But the current is not C. The current is 2 miles an hour. It tells us this. So this is the setup for rate. Time, we're going to do what we did before and express time as a distance divided by rate, because the distance in this problem, upstream it says 26 miles and 34 miles downstream. So the trick is I'm going to express time as distance divided by rate, 26 over b minus 2, and 34 over b plus 2. Now, the key words in this problem is same amount of time, which means that the 26 over b minus 2 should be equal to 34 over b plus 2. And if I multiply both sides by a least common denominator of b minus 2 times b plus 2, what I get is, let's move it up here, I get 26 times b plus 2 equals 34 times b minus 2. 26 and 34 are both divisible by 2, so I can divide both sides by 2 and get 13 times b plus 2 is equal to 17 times b minus 2, or 13b plus 26 is equal to 17b minus 34, or negative 4b is equal to negative 60, or b is equal to 15. And that's what it wanted. The boat goes 15 miles per hour. Okay, next one is a little tricky problem. This is a type of problem called a work rate. And the setup can be trickier. The solving is easier. But it says a tub can be filled by the cold water faucet in 8 minutes. The drain empties the tub in 12 minutes. How long will it take to fill the tub if both the faucet and the drain are open? Sometimes it's easier to see these problems as mixture problems. We have the drain emptying the tub, and we have the faucet filling the tub. So I'm going to put faucet, and then I'm going to put drain. I'm going to set up something just kind of like a rate time distance problem. We're going to have a rate. We're going to have a time that they actually work. And we have the distance, which is more like the number of tubs emptied. I'm going to call this jobs, which to me indicates how much of the job is done by the faucet or how much of the job is done by the tank. So basically that's kind of a thing. If we're trying to fill a tub, that would be one job, or if we're emptying a tub, it would be negative one job, and we have little fractions along the way. So again, it says a tub can be filled by the cold water faucet in 8 minutes. That means that the 8 minutes, if I kind of make this a rate, that is one job in 8 minutes. So the faucet's work rate is 1/8. 1/8 tubs per minute, or jobs per minute. The drain empties the tub in 12 minutes. That I'm going to put not just as 1/12, I'm going to put that as negative 1/12 because it is going in the opposite direction. Okay, the time we don't know. It says how long it would take to fill the tub if both of them are open. So I'm going to let t equal the time to fill, and I'm going to put in minutes because the units of this problem are in minutes. So I'm going to put a t here and a t here. And then if it's, well, jobs would be rate times time. So this faucet completes T over 8. The drain is negative T over 12. And the sum of those, T over 8 minus T over 12, the sum should be 1 complete tub. So now that we've got that, we can just multiply both sides by the least common denominator of 8 and 12. The least common denominator of 8 and 12 would be, well, 8 factors into 2 times 2 times 2. 12 is 2 times 2 times 3. So my LCD should be 2 times 2 times 2 times 3. 3 2's and a 3. And 3 2's and a 3 is 24. That's the long way of figuring out that the best denominator to do with 8 and 12 is 24. So if I multiply both sides by 24, I get 3t minus 2t is equal to 24, or t is equal to 24. So it takes 24 minutes. Next, this is a true story. Actually, it was true a couple weeks ago at the sectional. If both Coach Kinnear and me line the cross-country course, I don't even have my correct name on this. I must pause and fix that. So this is a little bit more of a complicated problem because it just has differences in time. And I'm not going to try to fix this, so just please put a Payne in there just to remind you that, yeah, change the last name. I stole this problem from when I did this in Algebra 2. And anyway, it says that I can finish the job in 2 hours by myself, and Kinnear would take 110 or 210 minutes. Remember, that is the same thing as 3.5 hours, which we're going to convert to 7/2 hours. So it wants to know time, so I'm going to let t equal the time we work in hours. And I'm going to do my own advice here and read this just once. Coach Kinnear and Coach Payne-Elliott line the cross-country course. Coach Payne-Elliott can finish the job in 2 hours by himself. Coach Kinnear would take about 3.5 hours to finish the job. If they start the job at 8:30 on this Saturday of the sectional meet, can they finish in time for the 10 o'clock coaches meeting? In any case, we're going to do the same thing where I have Payne-Elliott. And my work rate is 1 job in 2 hours. That's 1 job for every 2 hours. That's also the same as a half a job in hours. So this is going to be my rate. Kinnear's rate is 1 job every 3.5, which is 1 over 3.5. Or if I multiply the numerator denominator by 2, that gives me 2/7. So that's 2 jobs every 7 hours, 1 job every 3.5 hours. And that's the rate. The time, we don't know. So I don't know how much time each of us works. So I'm just going to put t for both. That's the variable we defined. And the distance is not the distance, it's the number of jobs like it was before. So multiplying that gives me t over 2. And this is 2t over 7. And if I take t over 2 plus 2t over 7, I would equal 1 complete job. Well, LCD here is 14. And if I multiply the left side and the right side by 14, I would get 7t plus 4t is equal to 14, or t is equal to 14/11, which is 3 3/11 hours. So can we complete the job in time for the 10 o'clock coaches meeting? Oh, sorry, that's not 3 3/11, it's 1 3/11. So basically what I'm asking is 1 3/11, is that less than 1.5 hours? Because 8:30 to 10 o'clock is 1.5 hours, and yes, it is. 3/11 is less than a half, because 5.5/11 would be the same as a half. So yes. Well, so let's say, can we finish the job? We'll say we finish since, and I'll just move this down, 1 3/11 is less than 1.5. So we do finish in time, barely. Lastly, crane alpha can unload a container in 10 hours, and crane beta can unload it in 14 hours. Crane Alpha started to unload it at 12 o'clock and was joined by Crane Beta at 1400. At what time was the unloading job completed? Well, with this one, let's do let T equal number of hours. We can just pick one. Crane Alpha works. So if that's the number of hours Crane Alpha works, and Crane Beta started 2 hours later, it's not T plus 2, it's T minus 2 because Crane Beta works for 2 fewer hours than Crane Alpha. That would be the number of hours Crane Beta works. That accounts for the time difference. Now let's do the same rate, time, and job analysis here. So we have alpha, we have beta, and the rate of Crane Alpha is 1 job every 10 hours, and the rate of Crane Beta is 1 job every 14 hours. The time of Crane Alpha is T, and the time of Crane Beta is T minus 2. So the number of jobs that Crane Alpha completes is T times 10, and Beta is T minus 2 times 14. If I take the number of jobs that Crane Alpha does and add the number of jobs that Crane Beta does, I would get the 1 complete job because we're unloading 1 ship. So the LCD here would be 10 and 14. That would actually be not 140, it would be 70. And 70 times the left side would be 7t plus then 5 times t minus 2 is equal to 70. Simplify the left side, I get 12t minus 10 is equal to 70, or 12t is equal to 80, or t would be equal to, so divide both of those by 4, I would get 20 over 3, or 6 2/3 hours. So I can say it takes, well no, it doesn't say it takes, it wants to know what time they finish. So T is 6 2/3 hours, and T was the number of hours that Crane Alpha worked, and Crane Alpha started at noon. So you can say they finish at 6:40 p.m., or if we're going to use 24-hour clock, like this problem is using 1840. That's it.